Good evening, students. Remember, if there's any part of this video that you didn't quite get, or if I went too fast, you can always, of course, pause it and rewind it and take a look at it again. We're going to continue looking at analyzing data. So far, we have learned how to display data. As you can see here, we've covered a lot of pictures. We are now going to focus on describing data. Does that mean with words? No. We're going to describe it with numbers. So let's take a look. One thing we want to know about the data set is the center of it. And there are different measures of central tendency, we call it. We have the good old mean, which also is called average, but we're going to call it mean in this class. There's the formula. Looks worse than it is, of course. This big E really is the Greek letter sigma, and it means to add them all up. So add up all the x's and divide by how many, and that's your mean. The median, the middle number. First, put your data set in ascending order. And if your data set has an odd number of values, then you have a middle observation, and that's your median. In this example, 7 is right in the center out of the 5 numbers, so 7 is your median. But let's add in a 6th value. We now have an even number of values. Okay, we had odd. Now we have an even number of values. We don't have a true center, so 7's not going to be the median. It's going to be the middle of the two. It's going to be the mean of the middle two. So the middle two numbers here are 7 and 10. And the middle of that would be 8.5. And finally, we have the mode, which is simply the most frequently occurring number. One interesting thing about the mode, though, is it's the only one of these three that can be used for describing categorical data. So let's say we recorded the eye colors of you guys in this class, and we had a bunch of blues, a bunch of browns, some greens, and some hazels. Well, we couldn't find the mean of that data set or the median, but we could find the mode, which I'm going to guess would be blue. Maybe we'll check that out tomorrow. Could be brown, too. All right, here's some things about the mean and median. The median is resistant to outliers. Here's an example. Let's take this data set again. The mean is 7. All right, it's the median, yes, but it's also the mean. If you added all these up, divided by 5, the mean is also 7. Throw in 99, so an outlier. It's much different than the rest of these, much higher. Well, the median was 7, and it just bumps up a little higher to 8.5. So the median resisted that outlier. But the mean, on the other hand, is non-resistant. It is very sensitive to those outliers. It's pulled towards the skewness. The mean in this case went from 7 to 22.3 by adding that one outlier in. And here's an example. This is why the mean is somewhat overused in our society. The median is actually underused. One place they do use the median is in average home price of a given area. So you're moving to an area, you want to know what the typical home costs in that area. Well, if you use mean, that is going to be skewed or pulled towards those real, say there's some big mansions in the area, some huge multi-million-dollar homes. The mean is going to be pulled and skewed towards that, and it's going to sound like the average home is kind of expensive. But the median, and they do use median home price, if you look around, will not be affected by those mansions or those very ritzy homes. But mean's not all bad. Mean's great. It can give us the sum of the observations, because if you use the formula, and if we know that the mean is 34 and we know that there's 12 observations, we can simply multiply 34 by 12 and we'll know the sum of all the values. All right, let's talk about, here's an example for us. Let's say that for a particular drug to be safe, a prescription drug, there must be no more than 46 milligrams of vitamin K For it to even work or be effective, let's say there must be at least 30 milligrams. So the range we want these pills to be are between 30 and 46 to be safe and effective. And this is somewhat true. Vitamin K is a vitamin our bodies need, but too much of it can be harmful. So let's say that we randomly took a sample of 11 pills off the assembly line and we tested those 11 pills. And remember, small samples can give us good information as long as we take it randomly. So we randomly pulled these 11 pills, and here's what we got. The mean was about right in the center of where we want it, 36.82 milligrams, and the median was 38 milligrams. So both of those numbers look pretty good in terms of safe and effective range. So do those pills seem okay to you? I hope you said no, because here are the pills. Are you still satisfied? Some of these people that are taking these pills with high amounts are going to be maybe doing that. So hopefully pharmacy is not in any of your futures if you said yes to those. But all kidding aside, what does this tell us? It tells us center is important, but we also need to know measures of spread. If I would have given you any measure of spread to this data set, that would have been a red light saying, uh-oh, these pills might not be safe or effective. So what are these measures of variation? One of them, the easiest one, is range. Range is simply taking the maximum minus the minimum. So if we would have done that with the previous example, we would have taken 55 minus 14. We would have gotten a difference of 41. The range is 41. So if you would have known the range to this data set, that would have been a red light saying no, these pills are not good. Another measure of variation is quartiles. It's much like finding the median. Well, you first find the median, and then you find the median of the lower half and the upper half of the data set. And that forms your 4 quarters of your data. So you have Q1 is the middle of the lower half of the data. Q3 is the middle of the upper half of the data. Now the IQR, that stands for interquartile range. That stands for the middle 50% of your data. If you subtract Q3 minus Q1, it tells you the range of the middle of your data. And that would also have helped us decide if these pills were safe. If we throw in the minimum and the maximum value, together that forms the 5-number summary. So if we would have seen the 5-number summary of our data set, we would have seen that we have a pill with very low amount, a pill with very high amount, and even the middle values would have been not so good except for the median. This 5-number summary forms our latest new picture, a box plot. And here's a nice picture of a box plot. Yes, it's also known as a box and whisker plot. So you can see Vixie over there with her impressive whiskers. But here's a picture of a box plot. Minimum, maximum, form your 2 whiskers. The box in the middle is formed by, bordered by your first quartile and your third quartile, and your median is the line in the middle of the box. You can also kind of look at these box plots and see shape of the data. If one tail is a lot longer than the other, that's going to be skewed in that direction. If it's all pretty symmetric, then it's probably the data set is symmetric. And there's our IQR, the middle 50% range of our data. Finally, we're going to have a way to test for outliers instead of just looking at a data set and saying, well, I think that might be an outlier, it may not be. If it's an outlier, it's going to fall more than 1.5 IQRs below Q1 or above Q3. We will calculate that in class, so I'll skip the rest of that for now. And I'll show you what a modified box plot is on the calculator. Let's take a look at that right now. Here's our data set of our pills. And how do we make a box plot on the calculator? Well, we go to stat plot, as you know how to do already. We put the data in the calculator first, of course, and we're going to turn this first one on. A box plot is, well, we have two of them. We have this one, which is a modified box plot. It shows outliers. It calculates the outliers for you, and it shows them as extra points. And here's our regular box plot next to it. We'll do a regular one for now. Hit enter on that. L1's good. Zoom 9 will be just fine. We don't have to customize it. And there's our box plot of our pills. If we trace, we can see the 5-number summary. Minimum 14. Q1 is 26. That means 25% of the values are between here and here. 25% are between here and here. Our median is 38. Our third quartile and our maximum. So there's a box plot on the calculator. And one final measure of variation, that is the standard deviation. It might be the most common one we're going to use, and it always pairs with mean really well. And really what it is, it's the mean of all the deviations. And deviation just means how far is each value from the mean. Standard deviation is always going to be 0 or positive. It can never be negative because the way we're going to calculate that will show you. If your standard deviation is 0, it means that there is no spread at all. That means all the observations are the same value, kind of like 7, 7, 7, 7. There would be no deviation from the mean. Therefore, the standard deviation would be 0. But you hardly see that in a data set. And it's non-resistant, unfortunately. Outliers do draw and skew the standard deviation to be bigger than normal. Let's calculate the standard deviation. Well, here's the formula right here. All right. Yes, it looks pretty crazy, but it's not too difficult if you put it into a table and calculate it piece by piece. And it's not as simple as plugging in a couple numbers either. Why? Because of good old sigma here. The Greek letter sigma means to add up a bunch of values. So this numerator is made up of the sum of a bunch of values, not just one number for each of these. So here's our data set. Let's use a small data set. The mean of these numbers is 7. Let's calculate the standard deviation. Well, notice in here it says to take each value and subtract it from the mean, or subtract the mean from it. How far is it from the mean? So let's take our first value, 3. 3 minus 7 equals negative 4. 6 minus 7 equals negative 1. Of course, 7 minus 7 is 0. There's no deviation there. Now we have our positive values. These are above the mean, and there you go. Now if you add these up, you get 0 every single time. The mean of the deviations is always 0 in any data set. That's the nature of the mean. So we can't really use that number. That's why the mathematicians of the past said, hey, let's square it. Let's take all these numbers and square it. We get rid of the negatives, and we can use that number. So if we square each of these and add them all up, we get 34. And that is the numerator of the standard deviation formula. So the sum of all the squared deviations is 34. See that? Divided by n minus 1, which is our n is the number of values in our data set. 5 minus 1 is 4. And we get the square root of 8.5. But since we squared our numbers, we're actually not in our original units, so we got to go back to our original units, and that's why the big square root is here. We have to go back to our original units. Let's say, for example, these were all in dollars. Well, this would be dollars squared. And that's not really, it doesn't make sense. So we go back to dollars, back to original, and we get a number that shows us the spread, one number that shows us the spread of our data set. So if you kind of look, with 7 being the mean, we have a couple values that are 1 away and a couple values that are 4 away. So the average of all of these is roughly, the average of all the deviations is 2.915. Standard deviation, that's how you calculate it. And that might be it for us today. Let me take a look here. Looking good. Hopefully you understood all this, and we'll talk more about this in class tomorrow.